In this video, we're going to analyze angle bisectors in triangles. So first, remind yourself what an angle bisector does. Recall that an angle bisector cuts an angle in half at its vertex. Also, remember the true distance between any two figures is the perpendicular distance. So any distance between these two lines is the perpendicular distance between those two. That brings us to the angle bisectors theorem. If a point is on the bisector of an angle, so in this picture BF is our angle bisector, then that point is equidistant to the sides of that angle. So this point F, its perpendicular distance to side BD and its perpendicular distance to side BE are equivalent. So FD and FE are congruent segments. The converse of that says if we know we have congruent segments, then we know that that is an angle bisector. So if we know first that FD is congruent to FE, and those are the perpendicular distances, then we can say that BF is an angle bisector. In these examples, we're going to use the angle bisector theorem to find each measure. So I want to find the measure of segment XY. So in this picture here, I notice I have congruent angles XZY and XZW. That means that XZ is an angle bisector. We also notice that XY is perpendicular to ZY and XW is perpendicular to ZW. So I know that XW is that perpendicular distance and XY is that perpendicular distance to each side of the angle. So therefore, because I know it's the perpendicular distance, I know those have to be equivalent from the same point X. So I know that XY has to be congruent to XW. Those measures have to be equal. Therefore, XY has to be 7. For the measure of JKL, notice here we aren't given that we know it's an angle bisector first. We are missing angle JKL, which is the other piece to JKM. We are given that segments JL and LM are congruent and that both of those segments are perpendicular to the sides of the angle. Therefore, we know that L is equidistant from the sides of the angle. Therefore, KL has to be an angle bisector. So because KL is an angle bisector, we know it cuts that angle in half. Therefore, the measure of angle JKL is equal to the measure of angle LKM. So JKL also has to be 37. Now, it's important to note, for this part here, only that JL and LM are congruent is not enough information to conclude that that's an angle bisector. We have to know that those distances are the true distances to the sides of the angle. So we have to know that those are the perpendicular distances. So it's not just enough to know they're congruent. We have to know that they're congruent and perpendicular. These three examples, I want you to try on your own. The picture for these three examples are angle BAD with AC between those two rays. Next, we're going to take a look at the angle bisectors on this triangle ABC. So once I plot those angle bisectors, notice that all three angle bisectors will be concurrent. And I can move my vertices around, and I can still see that they all intersect at this point here. No matter where I move those points, that point of concurrency that we just saw is called the in-center for the angle bisectors. The angle bisectors are always going to intersect at the in-center. And because it came from the angle bisectors, we know the in-center has to be the same perpendicular distance from the sides of the triangle. Now, because that is going to be the same perpendicular distance, to each side, we could actually draw a circle using the points that intersect the sides from the incenter. We draw that circle, and notice that circle is inside the triangle. So what we've done is we've actually inscribed a circle inside of a triangle. What we're going to do next is actually use the in-center theorem to find measurements. We want to know the measure of JF if J is the in-center of this triangle ABC. Point J being the in-center automatically implies the relationship between segments BJ, CJ, and AJ. All of those have to be angle bisectors. Now, those being angle bisectors also implies that we know those perpendicular distances have to be congruent. So by the in-center theorem, J will be equidistant from each one of the sides. So JD, JE, and JF will all have the same length. Now, because we know those are the same length, in order to find JF, I can find one of the other ones. I already have measures for AJ and AE, and those are two sides of a right triangle that's created inside here. So I can use Pythagorean theorem to help solve. So a squared plus b squared equals c squared. I know that 12 is one of the legs and 15 is the hypotenuse, and I'm looking for the other leg of that right triangle. So JE squared plus 12 squared equals 15 squared. Then solving Pythagorean theorem, I get that JE has to be positive or negative 9. But because a length can never be negative, we use only the positive square root 9. So if JE is 9, then we know JF has to be 9. Next, I want to find the measure of JAC. JAC is the angle here. Starting using the in-center theorem, we know BJ bisects angle CBE. Therefore, it's going to take two JBEs to be equal to CBE. So we know that this is 34 here. So 2 times 34 gives us 68 for CBE. We also know that DCF is going to be 2 of these 32-degree angles because JC also bisects angle DCF. So 2 times 32 gives us 64. Then I can use my triangle sum theorem to find the remaining angle A. So I know my 3 angles add to 180. So the 2 that I know are 68 and 64. Add those together and subtract from 180 and I get 48. But because 48 is the entire angle, I know that I need to divide that by 2. So 1/2 of 48 for each one of those angles that is bisected gives us 24 degrees. Okay, next I want you guys to try 4A and 4B using triangle XYZ here.